My name is Emma Carline. I'm an algorithm developer at Oceansonics, and today I'm going to do a presentation about a specialized hydrophone array that we're developing to measure sound from subsea equipment. This presentation was originally given at the Oceans Conference that was in Halifax in 2024. There's actually lots of equipment in the ocean. There are structures for the energy sector, ship hulls, and of course underwater vehicles. To give you a sense of the magnitude, this is a map of offshore fields in the North Sea, and there are more than 100 installations there. The problem is that subsea equipment wears over time. Early detection of issues is critical because unplanned maintenance or unexpected downtime is costly, and we want to avoid environmental impacts. The solution is to do regular inspection. Traditionally, inspection is visual, however, that doesn't catch everything. For instance, inside some of this equipment, there might be complex processes. However, if the equipment involves movement, then this often creates a sound. And changes in sound can indicate changes in the health of the equipment. At Oceansonics, we make hydrophones, which are underwater listening devices. Our hydrophones measure sound from 10 hertz to 200 kilohertz, which is ultrasonic, and that's the frequency range for detecting things such as leaks. Another advantage to measuring sound from subsea equipment is to understand how much noise it's injecting into the ocean. Studying underwater sound from machinery is not new. There was a previous study done by the company Naxos where they installed hydrophones permanently on subsea equipment. Some challenges, though, were limited bandwidth, and they were also limited to one location for the listening. Our idea is a little bit different, and that's to incorporate listening onto traditional inspection. Here's an example of some inspection footage, and if you add a hydrophone, this is what you would hear. There's a lot of background noise here, and that's because the hydrophone is on an ROV, and we'll talk about that challenge later. So adding a single hydrophone is interesting. We get to hear what the equipment sounds like. However, we also want to know where the sounds are coming from on the equipment, and that's where beamforming comes in. How beamforming works is it's a technique using a hydrophone array that focuses the array in the direction of to hear different sounds. So it adds time offsets to the array hydrophone channels to focus the array. If there is a sound source in the direction that is being focused, then the signals will constructively interfere, creating a loud sound level. If there isn't a sound source there, then the signals will deconstructively interfere. In the bottom right, this is an example of what happens if you do beamforming over a grid of points in the field of view using a two-dimensional hydrophone array. We call this sound mapping, and here the color is represented by, it represents the sound levels. It's a very intuitive way to represent sound source location. It's also frequency selective because the calculation is usually done in the frequency domain where it's faster. And sound mapping algorithms are an active area of research, and there's always more complex algorithms being developed to get better resolution or accuracy. Because it's frequency selective, we can produce sound maps for different frequency bands. Sound mapping is already being used in air. These are two examples of sound mapping arrays. We developed the Smart Underwater Sound Imager to do sound mapping underwater. This is the original SUSI array. One challenge with doing sound mapping underwater is that wavelengths are larger underwater, and this requires larger arrays to capture the same frequency range. However, to be included in inspection, we also needed the array to be mountable on an ROV, so this also limited the size. The geometry of the array, or the positions of the hydrophones, does have a big effect on the sound mapping performance. It affects two metrics: the beam width, which is a measure of resolution, and the dynamic range, which is a measure of the SNR of the array. For the original array we developed here, the size was just not practical. So we began a new development to make a portable array, a portable sound mapping version of this array. We were able to reduce the number of channels down to 16 and to shrink the diameter from 1.5 meters down to 0.55 meters. And we were able to do this, interestingly, without a loss in the sound mapping performance. And this was thanks to using a specialized beamforming algorithm developed by Robert Dougherty called functional beamforming. The early test of the SUSI array was to measure its sound mapping performance by comparing against predictions from a digital twin. The tests were done in the Halifax Harbour, and here we tracked a little ROV that had a sound projector attached below it, and the sound projector was playing pure tones. This is the results from those early tests. So you can see the sound map. There's a bright spot that's over the sound projector, and the array is creating that sound map by beamforming over that frequency band shown below in the spectrogram where the projector was playing tones. We realized that we could also map sound from the ROV itself, its motors, propellers. Those are lower frequency sounds, and this is the results. So this time, the bright spot is not on the projector, but it's on the ROV, as you would expect, because it's the thrusters and motor that are making noise. Baseline inspections were done using the SUSI array in June of 2024, this past year. The SUSI array was mounted on a work-class ROV that was doing the inspection, and this is a large-scale, 2-week inspection at 2 sites. The depth of the water was in the range of hundreds of meters. A rich data set was produced. There were many sensors on the ROV, and there was also data from the SUSI equipment. Going into this, we didn't know how loud the ROV noise would be. This is a new ROV, and at least it hadn't been used with the SUSI array before, and its noise was unknown. There was a chance that it could mask sounds from the SUSI equipment that we were trying to inspect. So to manage ROV noise, at the beginning of the inspection, we did an ROV noise calibration. And this was to capture sound from the ROV by itself, without the SUSI equipment, and also to try to find ways to reduce its noise. As you might expect, having the ROV stop and drift, not use its thrusters, reduced its noise. And one interesting way we found to reduce ROV noise was by turning off the ROV's hydraulic pump. This is an example of what it sounds like when the ROV pump is turned off. So once the pump turned off, the sounds that remained were sounds from the SUSI equipment itself. During the inspection, we had the ROV going into this quiet mode at distinct points. This added some time to the inspection, so we didn't do quiet points all the time. Finally, I'll present some results from that baseline inspection. I'll focus on one type of equipment. There were multiple pieces of this type of equipment, and we observed from the acoustic data that some of these had one face that was louder than the others. On the loud face, we found that sound located to the choke. So this is the quiet face. You can see in the spectrogram that the colors are darker, which means sound levels were lower. And the sound maps don't really show sound coming from anywhere. In contrast, on the loud face, the sound map is showing that you can hear that flow sound. It's coming from, looks like 2 sources, with one stronger source on the left side of that equipment. The metadata from that piece of SUSI equipment showed that the loud face was the side that had the choke on it. And that was consistent for all of the pieces of equipment that had a loud face. They were exactly the ones that were partially choked. To conclude, adding acoustic measurements to an ROV inspection can provide useful information about the condition of subsea equipment. And sound mapping is an intuitive way to show spatial information about sound sources. With the SUSI array, we found it's also possible to do this with a relatively small array. ROV noise can be a challenge. For future work, we want to better connect the measured sound to the equipment condition to understand what sounds are normal and what sounds are abnormal. We also want to iron out the process of quieting the ROV because having it stop adds time to the inspection. And finally, inspections are moving more towards using AUVs rather than ROVs. And this is a chance for better acoustics because the AUVs, they can go quite quiet when they're turned off or not flying. Thank you for listening, and I hope you enjoyed this presentation. If you have any questions, feel free to contact myself or my co-author, Mark Wood. Our email addresses are shown here.